To kick off here on our slides, my talk is entitled Analytics Through the Quantum Lens. Why analytics? Well, we're in the business, obviously, of quantum computing, hence the Q and the Q2B. And so we're all here to talk about quantum computing specifically. But if we kind of back up and zoom out a bit, maybe we can come to the understanding that we're not really in the quantum computing business, in a sense, if there is a quantum computing business. In any wide sense, that we would consider that there would be a computing business that's just about the computers. Actually, the computers are all meant to do something. And so really what we're really in the business of doing, especially with this new computing capability, is being in the business of making data-driven decisions, be those decisions using simulation in drug discovery or materials discovery, or decisions in other areas of the business on the commercial side, in marketing, in other areas where we want to use our data to drive business or other business-oriented decisions. And quantum technology clearly fits in this in that it helps us to create better models, find better optima, and uncover correlations that may not have been possible with classical computers. Quantum devices are exciting because they can help us create these better models. Quantum readiness, though, is the next step in our ability to actually create value from the data that we have. So I think it's important that we need to humbly really understand our position in the universe, which is increasingly fragmented, especially in compute and in data. And how does quantum really fit into that ecosystem, into that environment, particularly in the enterprise where these computers are first going to be used? And it's important to keep some perspective as we enter the next 3 to 5 years of development in this field, as we build support for our quantum initiatives, how we build software and hardware to actually be useful to enterprises, to governments, and to large institutions where quantum computers are sure to make their mark in the coming years. So how do we actually make it useful? So when we make this an analytics conversation, not about the compute and the special magical qubits that we have, and more about what we're going to do with it, it becomes less about the hype technology. Oh, we have the most magical qubits this month, and it becomes more about the how we're going to actually use this new compute, any new compute. This one happens to be quantum. There are different flavors of quantum compute. There are other exotic compute architectures out there that are emerging. So how do we use these things? How do you use these things together? And how do we find the advantage of quantum in this utilization by making use of this kind of future compute? So where will we find this quantum advantage, if you will? We increasingly look at this from an analytics perspective by focusing on nearer term use cases. And we find these, generally speaking, in data science and machine learning, where we believe increasingly that quantum can bring advantage, perhaps more quickly on a timeline that's relevant in production than in some other areas where quantum will eventually find an advantage. So these are areas like unsupervised learning, QGANs, QAANs, and these types of things. I think if you see some of our other talks this week, you'll see some pretty interesting news that we're dropping on this, and some stuff that's actually even visually quite appealing to show the potential of this area. But I think one of the things we need to realize here is that sometimes the value can be found in the quantity over speed. And this is what may allow data science and machine learning to find advantage, perhaps even more quickly on a timeline that's relevant to corporations and governments than some other areas of quantum advantage. The accuracy of the models, for example, using quantum as a source of randomness, and you'll be seeing some of that in our talks in technical detail. But this can really bring advantage in the way that we create our models, in the way that we are able to solve the problems using a quantum computer. There have been some papers that I'm sure some of you have seen on how a quantum walk is different from a classical random walk in the way that a quantum computer can approach a search or another model that is used to solve some other problem. So the way that the quantum computer can approach the DSML space can actually give an advantage that's not just about quickness, although that's a huge component of what we can do. But fit of the model, accuracy of the model is very important in data science. And this is an area where we believe that quantum is going to be bringing us a real production advantage on the nearer term. So how will we make quantum viable, though? How does it really actually become production ready technology? So in particular, I want to talk about 4 necessary shifts that I think we need to make quantum computing actually practical. And this is really important to make it tractable, to make it relevant, and to actually create business value. And these shifts are informed by our journeys at Zapata with enterprise and government customers that we've had in the last 2+ years that have really shaped our product requirements and have made us understand what is really necessary to make quantum actually useful and actually viable in the real enterprise. So the first shift that I'd like to talk to is basically a shift from an insurance policy. It's a shift of a frame of mind from making sure that we're not late to the party to actually building capacity. So many of our customers have been in the mindset of we're going to be disrupted by this. We have to get ahead of this. We don't want to be behind the 8 ball. But insurance is really not that helpful a frame of mind in the situation that we're in, because talent and capability building can't be done overnight. So you can't just be there waiting, doing a little dabbling as an insurance policy and expect to, do a couple of POCs, do the checkbox on your quarterly report to shareholders and think you're done. We have checked the quantum box. Really, the coming of quantum computing and importantly, other exotic compute as well, neuromorphic computing and other modalities, it's inevitable. It's happening. It's real. We're going to see things this week that show how real it really is. But because of this, we're going to have a proliferation of all types of compute. And we need to consider quantum computing as a part of our AI strategies and an integral part of those strategies while we build our infrastructure now, because this is probably the first on-ramp that we're going to see in quantum in business. So really, we need to move from just this insurance policy of trying to play to lose or not lose and shift to, and a little bit of my New England bias comes in here, but Tom Brady, well, maybe now it's a Florida bias. But true competitors are the ones who always play to win. And really, if you want to be winning in this space and winning with your infrastructure decisions, your compute decisions, and being data driven. Everyone says they want to do this, but really to do this, you really have to shift your mindset away from, okay, let's check that box, to how are we actually going to prepare ourselves for something that is sure to be very disruptive over the coming years. Does this mean that we can't have POCs? No, but we need to shift from just doing POCs into actually making our infrastructure capable for this. And another shift now that we have to think about is working slowly away from just the algorithms themselves. So, I have this neat way to solve a mathematical problem using a quantum computer, to how is that actually going to work in the real world in an actual workflow that involves real data, real outputs, real dashboards and UIX considerations that you're going to need to really deliver this to business decision makers. So, hardware is not going to live next to your data for some time. Circuit preparation challenges will scale classical requirements as the devices grow. So you're going to need more classical compute. So when you think about the workflow, you have to think about what your infrastructure is going to look like for the compute that's not just quantum, but also your classical compute. And spinning the Frisbee on the public cloud could become an expensive proposition as well. So that infrastructure decision has to be considered. Your data processing pipelines are already complex, I'm sure. And quantum won't operate in a vacuum that's immune from that. It's not going to get better because you're doing more compute. It's probably going to get worse. So all your data processing pipelines, cleaning, ETL, and that kind of thing is not going to go away. It's going to become a bigger problem, and you need to start thinking about that. So successful solutions are going to require collaboration between many authors. You're going to need a workflow architecture that helps people focus on their expertise, on their component, but be as part of a larger machine. The algorithm expert may not be the person who's the ETL expert for doing supply chain management. They may not be the person who has an expertise in logistics or in operations research. They may not be the PhD in operations research that you have in your logistics area, or the marketing expert. But the quantum algorithm person needs to be able to work on their piece of the puzzle. So a workflow, a holistic method of doing this is going to be increasingly important. Workflows actually do not require that you create a new breakthrough in every area. You can combine things from other users from the public source community, and you can abstract yourself away from the intricacies of every little part, because it's true that not every single company is going to have 50 quantum algorithms experts on staff. That's just not going to happen. It doesn't happen in classical data science that we always have 500 PhDs in every industry working on the data science algorithm components. So we need to be able to use a workflow system that will allow us to take these components and use components that other people have created for us, and also work as a team. And our newest quantum algorithm is not always necessarily going to give us a speed up. Let's also realize that it may be where you have to put into parallelism into your ETL, into your other classical parts of pre-processing that really help you get the speed up. It's no use for us to have a computational speed up on a system that's slowed down by data cleaning types of procedures because you haven't built the infrastructure for that with your data science. So we have to think about this all holistically as a total workflow. And this is what a quantum workflow actually is going to be. This is the VQE algorithm as we've implemented it. The quantum piece is that little pink cloud on the right there. The rest of it's classical. So in container language, there are about 40 containers here, but only one of them is quantum. The rest of it is a complex mess, if you will, of classical processes, one of which we oftentimes run on an HPC stack because it's highly computationally complex in and of itself. A pre-processing step on an HPC computer necessary to load things for the quantum computer. So this is reality. This is the messy reality of what actually happens when you put this stuff into action. So everyone is concentrating now, I think, on that little pink box, but the algorithmic step is necessary, but not sufficient to give you the total solution. In addition, if you kind of zoom into all of this, we really have to shift ourselves from a fragmented universe to a unified universe in order to be able to take advantage of what we're talking about. And this is related to the previous graphic, but not just on the compute frame, but also on the data frame. Because we have this fragmented data universe, and we have this fragmented compute universe where we have to use all those different components that we just saw together in some kind of organized manner in order to take advantage of the advantage that quantum is supposed to give us. And so it's really necessary to move from this mess into something that looks more like a workflow that organizes this mess and abstracts us away from the nitty gritty of the enterprise data swamps and compute swamps that we're building, and allow us to act in a more efficient manner when we create our models and when we reuse tasks that are in our model. So the current state is not good enough, and we do see a huge proliferation of compute choices, data architectures, and we really do need to be able to orchestrate and unify these things in some kind of a cognizable workflow type of a layer that abstracts us away from the mess to make any use of this in production. And we're finding this in classical data science, but it becomes even more true when we're trying to combine different kinds of compute to make a quantum workflow actually function in reality. And then the final shift we think is about shifting from an exploration mode to an operationalization mode. So from tinkering and exploring and saying, isn't this neat, into an operational mode in which we think about what is our infrastructure going to look like. We're quickly approaching a regime that we'll see in a lot of talks and data that will be presented. We're on the trajectory to be able to deliver quantum advantage in a time frame that will affect change in our organizations in the time that we have our midterm business plans built for. And therefore, we need to start thinking about what are the choices we need to make in order to take advantage of these things. If we don't start operationalizing now, it will be too late. You cannot just wait for that shiny fault-tolerant computer to show up 5 years from now and think you'll just hit the big quantum easy button and all your data needs will be solved. That's just not how it works. We've learned this from classical data science and machine learning. It just doesn't work that way. And it's very easy to fall behind here. It's not just about model creation, iteration, but going into quantum ops and AI ops. And this includes, as we've alluded to and seen here, the pre and post processing. That's really important. And that includes data and compute, ETL jobs, and multiple types of computes in the same workflow. You need to consider where your data and where your compute sit. Are they in public cloud, private cloud, on-prem, HPC resources? And you need to start thinking about how that is going to be organized. Gartner spends a lot of time educating us about our need to focus not only on better model building, but model operationalization, because an alarming percentage of models developed for deployment are never actually operationalized. And quantum makes that decision-making process and this shift much more important and much more acute, because we're not just talking about pre-existing things, pre-existing algorithms from the classical world. We're adding a new level of complexity, some things that are even at certain regimes not testable on classical computers. So we really need to be careful about being able to operationalize at scale our models so that this can actually become a production technology and not just something that is really cool, really neat qubits that just winds up on a shelf somewhere. So to make this shift viable, to summarize, we need to shift from insurance to building capacity. We need to shift from a focus on algorithms and the neat math tricks we can do to how that actual workflow is going to work in practice. And we need to work to increasingly unify these fragmented worlds of heterogeneous compute and heterogeneous data and data location. And finally, we have to move from a mode of exploration into a mode of operationalization, probably quicker than we all realize. So what can we do today? Engage scientists to identify AI ML problems, create workflows from real data and sources in hybrid quantum classical compute modalities, and deploy quantum or quantum-inspired workflows that are forward compatible to quantum. And hype, finally, is our shared enemy. I think we all need to avoid the hype where we can and be real about this, because this is a lot more difficult than we all think. Any questions? Thank you.